Hello, fellow humans, and welcome to the first coding challenge. This is going to be a YouTube series every Wednesday where I do some sort of coding challenge. The idea of it to be probably less than an hour, but to go into some sort of depth about what I'm doing. So the first week, we're going to be making Game of Life. Second, maze generation. Third, we're going to do some smart rockets. And then fourth, I was thinking about doing some snake AI. And then, of course, later on, we're going to be doing some more. But this is just a rough draft for now. So let's jump over here and let's discuss what John Conway's Game of Life is. So over here, I have the Wikipedia article open for John Conway's Game of Life. And John Conway, he was a mathematician. Back in 1970, he devised this cellular automaton. And the way that his Game of Life works is it is an infinite two-dimensional orthogonal grid of square cells, each of which has two possible states. It's either alive or it's dead. So in this example up here, these black squares are representative of the alive cells, while the white background are all the dead cells. And every cell interacts with its 8 neighbors around it. So if you have an orthogonal grid, something like a little tic-tac-toe grid, this middle cell here, this little box, it has 1, 2, 3, 4, 5, 6, 7, and 8 neighbors. So the cell in the middle here, it does have 8 neighbors. And the way that John Conway's Game of Life works is that depending on the number of cells in these 8 neighbors that are alive, something happens to this cell. And the rules say that any alive cell with fewer than 2 neighbors dies, any live cell with 2 or 3 neighbors lives on, any live cell with more than 3 neighbors dies, and any dead cell with exactly 3 neighbors becomes alive. So in our little example over here, if we have a cell, and then it has 2 cells next to it that are alive, so this one is alive, this one alive, and this one is alive, and we're looking at this cell in particular, then the next generation, this cell will stay alive. And then these 2 cells, they also have 2 neighbors next to them. And then this cell right here, that's dead currently, it has 3 cells alive next to it. So the next generation, it will become alive. Hopefully that makes sense. And we're gonna go ahead and start to program this. So the first thing that we're gonna be doing is we're gonna be needing to have some sort of grid. So we're gonna take the window of the screen and divide it into many different cells. Something like this. And then we're gonna have each of these cells be represented by an object that keeps track of where it is on the screen, and as well how many neighbors it has currently alive. So let's jump into processing and let's get started. All right, we're over in the processing environment right now, and if I go ahead and run this sketch, all it is it's going to bring up a blank canvas that has a grayish background to it. So the first thing we said we were going to do is to try to subdivide this canvas into a grid of cells. So I'm going to go ahead and create a new class called a cell, class cell. And this will be the representation of the boxes in our grid. So we're going to create the instantiation function. And we're also going to create an update function. And we're going to create a function that shows where, or shows the cell on the screen. And then in our main function area, we want to have an array of these cells. So we can say, okay, I want a cell array, and it's going to be a 2D array because you want to have both an X and a Y coordinate. And we're going to call this our grid. And then our grid, after we define the size, it's going to be instantiated as a new cell array that has dimensions of width divided by some number, which we're going to define up here as our cell size. And then let's go ahead and set it to 10, just for now. So we're going to have width divided by that cell size. And then we're going to have our height divided by that cell size. Now that we have the size of the grid, it is time to populate the grid with the cells that we've created. So we're going to have a for loop, which goes from 0 to our grid size, which is grid.length. And then inside of the first for loop, we're going to have a second for loop. Because we're doing a grid, we have to do for every x, do every y. So we're going to have an integer j start from 0, which goes from our grid at the position I dot length, or goes from 0 to the grid at I dot length. Just like that. And then, let me close that for loop. And then, now that we're inside of this double for loop, we can say, okay, grid, at the position I, comma, j, I want there to be a new cell. Perfect. But there is something missing here. We should let our cells know what position they are on in the canvas. So we're going to have it represented by a p vector, and we're going to call it position. And then when we create our cell, we want to tell the cell what position it's at. So it's going to take in an integer x and an integer y. And then it's going to set its position to the values given. So x and y. And then for now, we just want to show them on the screen. So in the cell's show function, we're just going to draw it as a rectangle. So we're going to say rect, and it's going to be at its position x and its position y. And then the size is going to be the cell size that we defined in the previous file. Just like that. Now if we go ahead and run this, we get an error because we haven't updated the previous function. So there is no cell function that has no parameters. We just updated it, so it needs to have an x and a y. So let's go ahead and change that. So it takes a I and a j. However, since I and j, they start at 0 and go to grid.length rather than going to the screen, let's go ahead and multiply them by cell size. Actually, now that I'm thinking about it, let's go ahead and keep them at I and j, and instead, when we show them, we take position.x and we multiply it by the cell size. And position.y, multiply it by the cell size. There we go. Now, if we run this, nothing should happen because we're not actually showing the cells. So let's go ahead into our draw function. And we can say we can copy this for loop and paste it into our draw function. And instead of setting each grid space to a new cell, we'll just say dot show. And call it like that. And then when we show the cell, because we actually want to see them distinctly, we'll just say fill random 255, just so that we can see them. And then we'll say no loop down here so it doesn't go crazy and like look flashing lights. And we'll go ahead and run it. And you can see now we have a grid of a bunch of little tiny cells populating it. All right, good. So this is a great start. I'm going to change our cell size from 10 because that seemed a little small. I'm just going to double it to 20 and we'll see how that looks. This looks much better. So we'll keep it at 20. And then now our next step, now that we have our cell grid, now we need to decide, okay, so each cell is either alive or it's dead. So let's go ahead and have some Boolean value decide if the cell is live or dead. So we'll go into our cell file and we're gonna have a Boolean value that's gonna be called alive. And if it's set to true, the cell is alive. If it's set to false, the cell is dead. So we're just gonna have it be totally random at first. So we're gonna say alive is going to be equal to random of 1 is less than 0.5. And then this should give every cell a 50% chance of being either alive or dead. So now instead of filling it with a random grayscale color, we can say if the cell is alive, then let's go ahead and color it white. Just like that. Let me fix my spacing. Otherwise, the cell must be dead. So let's go ahead and fill that cell as black. Now if we run the sketch, every cell should be either white or black, and it looks like about a 50% chance of either any one cell being alive or dead. One thing that we can do for efficiency is instead of making the cells draw a rectangle no matter if they're alive or dead, we can change it so that they will only draw a rectangle if they are alive, and if they're not alive, they don't do anything at all. And this should look exactly the same if we go ahead and change our background to 0. This should look exactly the same as before. However, we're only drawing the cells that are alive and we're skipping the ones that are not. However, this simulation isn't doing anything right now. It's just a grid that has some cells that are white and then some cells that are black. So the way that Game of Life works is that there is a concept of a generation. And for our purposes, we're just going to have that be the draw function. So this draw function loops 60 times every second, and then that will be our generation. And in each generation, if you remember, any live cell, so it's going to die if it has more than 3 neighbors or less than 2 neighbors, and any dead cell is going to become alive if it has exactly 3 neighbors. So now we have to figure out some way of implementing these rules into our processing sketch. So the first thing we're going to do is go to our cell class, and then we're going to create a new function. So we're going to say void, and we're going to call it getNeighbors. And the idea behind this function is that this function will go ahead and count the number of neighbors that the cell currently has. And the way that we're going to be storing that is we're just going to have it be as an integer, and we're going to call it neighbors. And the way that we're going to be getting this neighbors value is we do have the position stored as a p-vector value. And if we go ahead and come over here, any cell in the grid corresponds to some x and then some y. And then it wants to check each 8 of its neighbors and then count the ones that are alive. So if this cell is at x and y, and we want to look at the cell that's diagonally to the left of it, we're going to look at the cell that has position x minus 1 and y minus 1. And then we're looking at the ones directly above. It's going to be at position x, y minus 1. The one to the right is going to be at x plus 1, y minus 1. And then so on and so forth until we've counted each 8 of its cells. Alright, so our getNeighbors function is going to have the name. It's going to start every time it counts. It's going to say, okay, our neighbors count. We're going to reset it back to 0 before we start counting again. And then it's going to go and iterate through each of its neighbors, which we saw how to do that over here. So we're going to start at x minus 1 minus y minus 1, and then work our way towards x plus 1, y plus 1. So we can do that in a for loop. So for I is equal to position.x minus 1, and it's going to go until it gets to I equals position.x plus 1, and increase every time it goes. And let's go ahead and set I to an integer. Alright, we had an issue where position.x is stored as a float, and that's because it is a p-vector value. So I went ahead and just casted it as an integer, and that should be fine. So we're going to go ahead and do the same thing. So we can copy that, and instead of I, we're going to say j, and instead of x, we're going to say y. Not j, y. I'm going to go from y minus 1 to y plus 1. Perfect. Inside of our for loops, we want to go ahead and increase the neighbor's value if the cell corresponded to the positions that we have is alive. So if grid at I comma j dot alive, if that particular cell is alive, then we can say neighbors plus plus. And that should count all of the neighbors. But there is one problem with this. There's actually several problems, but one problem is that it's going to count itself. So if we go back over here, the cell here, if it goes x minus 1 to y to x plus 1, and then over here at x minus 1, and then it's going to get to here where it's going to be exactly the same cell that it's counting. So there's a couple of different ways we can solve this. One way we can solve this is having if grid at ij.alive, but also and I does not equal to pos.x, and j does not equal pos.y. And then we're going to go ahead and encapsulate these so that they're together and negate it. So if the grid is alive and I equals position.x and j equals position.y is not true, then we can increase the neighbors. There is one other issue with this, however, as well. If we go back over here, say we're looking at a cell right here. So it's got these neighbors, 1, 2, 3, 4, 5. Because these don't exist over here. There's nothing here, here, or here. So how can we tell the grid to grab those spots if they don't exist? It's going to give us an error, and we don't want that. So the way that we fix this is we say, okay, if I is greater than or equal to 0, and j is greater than or equal to 0, and I is less than grid.length, and j is less than grid at I.length. And the reason that we do this before we call the grid function is we don't want processing to try to access a spot in the memory that doesn't exist. So we put it before to try to catch it. And then we're gonna say this is double and that should be pretty good. So let's go ahead and show that in some way by having that display as text above the cell. So we're going to say text, and it's going to just go ahead and print out what neighbor value it is. And it's going to be at this position here. Just like that. Perfect. So let's go ahead and come back into our draw function. And then we want to count the neighbors before we show them, because it's not going to loop. So let's go ahead and say, I think it's called count neighbors. It's called get neighbors. So we can go ahead and say dot get neighbors. And let's go ahead and run it. And then now we can see some sort of representation about what it's processing. However, all of these numbers seem completely wrong. So let's figure out why. Alright, so I just went ahead and ran it and realized that there was a couple of issues, but I went ahead and fixed them, and I'll walk you through what I did. First off, I went ahead and set the text align to be centered so that the cells are centered, or that the text inside of the cells are centered. And then inside of our for loops, I changed the less than to a less than and equals because it wasn't counting any cells to the bottom or to the right of it. So now it should do that. And then in our show function, I put the text underneath where it was alive and made it bright red so that you can able to see it. And now when we run it, you can see that it runs beautifully. For any cell, it has the number of alive cells next to it. So for this dead cell here, it has 1, 2, 3, 4 neighbors, and it represents it perfectly. Now that we have a way for the cells to know how many neighbors they have, now it's time for the grid to update based on the neighbor count. So we no longer need this no loop, because each loop that this goes through is going to be another generation. So the way that we're going to do that is we're going to have a new function. We're going to call it void next gen. And then every frame, we're going to go ahead and call next gen. And the reason I'm doing it in a separate function is just so that it's cleaner and I know where to go if something goes wrong. So our next generation is going to loop through all of the cells and determine if they are going to be alive or dead in the next generation. So we're going to need a new cell grid. That's not an L. We're going to need a new cell grid, and we're going to go ahead and call it next. And then we're going to go ahead and... Actually, instead of it being a cell grid, we're going to be a Boolean grid. Because there's no reason for all of the cells to create new cells when we can just have Boolean variables representing if they are alive or dead. So we're going to go ahead and start looping through all of the cells, which we already have code for. So we're just going to take this code, copy it, and paste it in here. And then we no longer need to get the neighbors before we show them. So we can go back into our cell, get rid of the code that shows how many neighbors they have, because we already know that that works. We don't need to debug it anymore. And instead, we'll just have it get the neighbors before we do any calculations to it. And then, now we can start our processing. So, if we remember from the rules, any live cell with fewer than 2 neighbors dies, any live cell with 2 or 3 neighbors lives on, any live cell with more than 3 neighbors dies, and any dead cell with exactly 3 neighbors lives. So let's start with a dead cell becoming alive when it has 3 neighbors. So if grid at I, j dot alive, if that is equal to false, So if the cell is dead and... Oops. There we go. And grid at ij dot neighbors, if that is equal to exactly 3, then in our next grid at ij is going to be set to true. I'm just now realizing that we need to actually determine our next grid, so it's going to be equal to a Boolean array that has the same dimensions as our grid, so grid.length. And then grid, I'm just going to say at 0.length. Because it's a square, so it doesn't matter which one we go for. And this is giving me an error on class. Next Boolean. Oh, it's going to need to be a new. There we go. And then, so now we have, in the case that the cell is dead and it has 3 neighbors, it becomes alive. However, there's if else if the cell, let me just copy this whole thing here. So else if the cell is alive, so this will be set to true. And the neighbors is going to be less or greater than or equal to 2. And grid at neighbors is less than or equal to 3. So either 2 or 3, and I can actually say double equals here. So if the cell is alive and neighbors is 2 or 3, then the next generation cells will also be alive. However, if we also want to say when they die as well. So now, if the cell is alive and the neighbors is less than 2, or neighbors is greater than 3, actually, we can just say, instead of doing it this way, because we're dealing with all these, either when a dead cell becomes alive or when a live cell stays alive, we can just have it say else next at I, j, set it to false instead. And then that's pretty much all that this function does. All that is left to do is, after all of that processing is done, we're going to loop through the values again. And we're going to say, instead of grid at I, j dot show, we're going to say grid at I, j dot alive is going to be equal to next at I, j. And then that should be it. So let's go ahead and run and see if anything went wrong. And it looks like something went wrong. Let me go figure out what it was. Alright, so it wasn't that bad of a fix. I just changed the logic here from equals to 2 to greater than or equal to 2. Because what I was doing, it was never equal to 2 and equal to 3. So greater than 2, greater than or equal to 2, and less than or equal to 3. So that should work properly. And then one other thing I'm going to do is I'm going to change the cell size back to 20. And then in our setup function, we can get rid of text align because we no longer need it. We're also going to set the frame rate to something that's easier seeable. We're just going to set it to 10 for now. And then if we go ahead and run this, you can see that we now have a functioning game of life simulation. Perfect. I think this went pretty okay. Now, if we want to, we can mess around with this a little bit. We can set the size to be something super small, and then we can really see it be in like all of its glory. You can take this project and make it anything you want to. This is just one example of a cellular automaton. You can change the rules however you'd like to. Instead of cells becoming alive on 3, what if they only became alive on 4 and they had to survive until they had exactly 3 neighbors, 4 neighbors, or 5 neighbors? Something like that. This whole idea of cellular automata has a huge community that are always exploring it and trying to make it something exciting to look into. So I recommend that you all go ahead and look into it yourselves. This project is going to be available for you guys to download and look at on my GitHub. Link is in the description below. And I hope you all have a wonderful day. Take care.